Hi, welcome back. It's me, Trash Puppy. This is part 2.1 of my devlog series on NetPuppy. If you're wondering why 2.1 and not just part 2, that's because I released part 2 not long ago and then quickly realized that some of the claims I was making about Python and concurrency in that video were wrong. So since then, I've regrouped, learned a little bit more, and now I'm coming at you with a better version of part 2. We're going to be talking about NetPuppy and how I tried to implement concurrency using Python but decided to switch to Golang. We'll just touch on basically how concurrency is actually a very difficult computer science subject and how I've been tackling it since then. All right, so if you remember from part 1 of this series, in writing NetPuppy, I've gotten it to the point where the two peers can send simple messages back and forth to one another. But I started to notice that there were a couple of weird bugs. A good example of one is that when one peer would send a message, it couldn't immediately send a second message until the other peer returned its own message. And that's because the two peers were blocking each other and the tasks that they were trying to perform on the socket were also blocking each other. Now, to understand, for me to explain what I mean, I have another diagram, but basically this ends up being the reason that I needed threading for NetPuppy. So let me show you this diagram that I've written up. All right, so if we pretend that this is NetPuppy, the program, when the program executes, it becomes a process. And what that means is it's given its own process ID, its own memory allocation, etc. So you can think of a process as basically just an executing instance of the program. So the main tasks that NetPuppy does and the tasks that end up blocking each other are these three I/O or input-output tasks. So the first one is NetPuppy reads from the socket. The second one is that it reads input from the user. And the third is that it writes to the socket. Now the problem with all of these tasks is that they're input-output oriented. So for task 1 to finish, it has to read data from the socket. It has to wait here until there's data to read. And that's the same for the other two. This one has to wait until there's data from the user, and this last one has to wait until it has written all of the data to the socket. So when task 1 executes, until there's data and it's able to read it all, it cannot return back to this main execution thread, right? Without concurrency, this is why these tasks block one another, because these other two tasks, 2 and 3, cannot start their execution until task 1 has successfully read data and returned back to the main task. So with concurrency, the reason that I needed it is I wanted to be able to start task 1, and if there wasn't data in the socket yet, I wanted to be able to return back to the main execution thread and start task 2. And if task 2 wasn't ready yet or hadn't finished because there's no data from the user, I wanted to be able to return and start task 3. That's essentially what concurrency would give me. I could start task 1, and while it's waiting for data, start task 2. While that one's waiting for data, start task 3. So all 3 of these things could be going and working without, they could all be working independently of each other. So now that I've learned that what NetPuppy needs is concurrency, it's time for me to figure out what the heck that actually is. Because at this point, I don't actually know anything about concurrency. So I go on to this whole deep dive into Python concurrency and end up learning a lot. So I'm going to explain to you my understanding of concurrency, but it is a very difficult subject in computer science. So I want you to take what I say with a grain of salt, because I've already messed this up once. And even though I'm trying my best at understanding and researching these things, I could still get it wrong. So there are a few ways you can handle concurrency from what I understand. One way is with threads and multi-threading, and one is with processes and multiprocessing. The difference between the two is why I originally decided to switch from Python to Golang. So I have another diagram for you, and we're gonna go check that out. We're gonna talk about multi-threading first, but what I wanna say before we start is that there are different types of threads, and this is partly what confused me about threading in the first place. So there are kernel threads and there are user threads, and I'm going to do my best to explain the difference between them. We're going to start with kernel threads. Every process has at least one thread. That's the main thread, and it is a kernel thread. Now, what that means is that the kernel space or the operating system has full control over that thread and how it eventually gets executed on the CPU. So when the operating system is running multiple processes, the way that it's able to run them all in what seems like a concurrent or parallel way is it has full control over swapping out the threads as they're running. What I mean by that is that it uses something called time slicing to choose which threads get swapped out for execution. Now, we're not going to get too deep into the weeds on time slicing, but basically the way it works is each thread that needs to be executed on the CPU gets a slice of time for that execution. So if this thread is executing on the CPU right now, if its time slice ends before it finishes, the CPU is able to interrupt that thread, pause it at exactly the point that it's at in its execution, and swap it out for a different thread. Now, that doesn't mean that this thread just disappears and goes away. Because the CPU can remember exactly where it was paused in its execution, it can actually come back and resume at that exact point this thread's execution, just in a new time slice. Now that we understand what a kernel thread is, we kind of have an idea of how the kernel and the operating system handles concurrency. So let's go over to user space and talk about how we can handle concurrency with user threads. So the main difference between a kernel thread and a user thread is that user threads are managed and created by our program. The operating system has no idea that they exist and has no control over their scheduling for execution until they cross over into kernel space. And what I mean by that is that, let's say we assign each of these threads to a task in our program. In order for these threads to be executed, they have to eventually be mapped to a kernel thread. So let's say these are our kernel threads. Now, there are a few ways that a system or a program or a language can handle mapping the threads. The first way that we're going to talk about is called a one-to-one mapping. A one-to-one mapping is nice because for each user thread from our program, we can use one kernel thread. We have access to one kernel thread, so for each of our threads, which is really nice because there's no sort of sharing hardware or having to deal too much with the concurrency. The next way that you can map, or that a system can map these threads, is with an M-to-1 mapping. Now, this way is not so good. It basically means that for our many or M threads in our user space, we only have access to one thread in the kernel space. So it's going to look a little bit more like this, right? Each of our threads that we want to execute in a concurrent way only has access to one thread. So we're going to have to handle a lot of the logic when it comes to the concurrency part over here in our program. We're going to have to do a lot of the logic as far as who gets scheduled first, what causes a thread to be paused in execution, how to swap them out, etc. Because once our threads, or however we've lined them up in our program, once it crosses over into kernel space, the CPU and the kernel is going to have full control over their execution, like we were talking about earlier. By the time they get over there, we have no say. All right, so the last way that we can map our threads to kernel threads is called, this is a little tedious, it's called an M to N mapping. With an M to N mapping, let's say we can bring one of these threads back. We have M mini user threads to N mini kernel threads. So let's say NetPuppy has its 3 threads. Now we have 2 threads, we have 2 threads that we can play with when we want to map them. Sorry, this one turned white, of course. Boop, boop. So it's a little better than an M to 1 mapping because we have a little bit more access to the hardware and more resources for handling our concurrency, but we're still gonna have to handle some of the logic of which thread or task gets scheduled and how over here in our program. So now that we understand how kernel threads and user threads help us do concurrency, let's bring it back to NetPuppy. So the original reason that I ended up switching from using Python to Golang with NetPuppy is that I completely misunderstood how Python does threading. At first, even after doing a bunch of research and cross-checking different resources, I thought that Python wasn't able to do threading at all. But it turns out that it can. However, it's still in a way that I personally think is less efficient than with Golang, and so I'm still happy that I switched to Golang. So let's talk about Python and how Python devs tend to do concurrency, because they tend to use multiprocessing instead, and there is a good reason for that. With Python, you have something called the global interpreter lock, and what this does is it sort of forces an M-to-1 system when it comes to mapping your user threads to your kernel thread. So no matter how many user threads you have over here for each of your tasks that you want to run concurrently, you are forced to use one kernel thread when it comes to the execution. So Python has a lot of libraries to help you do this. The two that I know of are called Asyncio and threading, but no matter what you do or how you end up handling the scheduling over here in the user space in the program, you're still going to be limited to one thread when it comes to execution, whether or not you could technically have access to multiple kernel threads. So a lot of people get around this when writing Python by using multiprocessing instead of multi-threading. With multiprocessing, we don't assign each task a thread. We instead break our process and its tasks down into little sub-processes, because each sub-process gets its own lock. The GIL does not lock every process that is a child process of your main process. So if you break each of your tasks into a little process, they each have their own GIL, and it's not so much of a big deal that it's limiting you to one kernel thread, because now your process, which needed 3 threads, are being mapped to 3 kernel threads. The problem with this, and the reason that I ended up switching to Golang, is that this is not that efficient, because each time you break this into another sub-process, like we talked about in the beginning, that sub-process gets its own process ID, its own memory allocation, and becomes its own independent little thing that's happening in your computer. There's a lot more overhead that goes into that, especially if you want each of these to be able to talk and share data. Now they're all in different, working and executing in different parts of the memory, and it just is less efficient to try to get them all to be working together. Even after learning that Python can handle multi-threading, I'm still glad that I ended up switching to Golang, partially because I like that Golang does an M-to-N mapping of user threads to kernel threads, and that means that I don't have to do multi-processing in order to get access to more kernel threads with NetPuppy, but also because since switching, I've noticed that languages like Python and JavaScript, which I was primarily programming in before, were abstracting a lot of these lower level concepts away from me, and that was actually making programming harder, I think, because since switching to a language like Golang, where it's like my responsibility as the programmer to handle the lower level things like making the threads and making sure that they're all running or whatever, it's made understanding my program a lot easier. I can make a mental model of what's supposed to be happening a lot easier, and my program's not doing anything that I don't expect it to do or that I didn't tell it to do. Whereas I feel like with Python and JavaScript, there was a lot more of that. It was harder to understand what it was doing because it was sort of hand-holding me through things like concurrency, and a lot harder to picture what my code was supposed to be doing. So I'm actually really happy that I'm switched to Golang, and it's been a lot better. But I think this is where I'm going to end this devlog. Next time we'll talk about how I finally did implement concurrency with in NetPuppy using Go routines and channels, and we'll also talk about how I finally got the reverse shell to start and be executed on the target. So that's going to be a fun one. But until then, thank you for watching this, and I will see you next time.